let me go back to the notes from last class because I'm going to reuse some bits here today, and we're going to pick up where we left off. So what I want to do is just reuse this same notebook because that saves us from having to type everything again. Okay, so what we could do, actually, let me teach you some other tricks that we're going to maybe find useful. So I'm going to make a copy of this notebook. What happened in the list of notebooks? Now I have, notice class 10, the icon is green because it's still running, and class 10 notes copy. And that copy is over here. I'm going to rename it class 11. And I'm going to add here regression because now we have two notebooks from today's class, and the name of the file is helpful for you in the future to find the material that you want to review. So what I'm going to do, I'm going to re-execute the cells that we want to still work with, the input statements, the cell that loads the data. I'm going to cut that cell because I don't need it. That was the cell that was showing how to pull up the help page, the manual page for a function. I'm going to re-execute that, which produced the plot. And this is the material about linear regression that we had copied in there. And I'm going to delete this discussion about functions. I'm going to delete that, that, and I'm going to go back to the linear narrative that has to do with the regression part. Okay, so we've executed up to here. This is material, text material with equations. Something else you might want to do when editing a notebook in this way is I notice this markdown cell now has very little material. I might want to perhaps merge the cell, merge with the cell below, and then all the markdown is together in that markdown cell. That is another thing we often do. Notice this is left from last class. So it says input line 12 here, but when I re-execute this line, it will show me input line 4 because that is the sequence of execution in this session. So even though the Jupyter Notebook loaded with code and output from last session, this had not been executed, and now it has. I've just executed now. So now we have available a custom function that we worked on last class. This custom function computes the mean value of an array. So this cell here defined the function, but the code that is inside has not been executed until we call the function. In this line, if I execute that, I notice the execution sequence now shows me input line 5 and right after input line 4, and the output is the value, the mean value of the year. Okay, the year array that I created. When did we create the year array? We created it right here, where we use numpy.load.txt with the file name. Some of you have a file name without the CSV. Some of you had a file name without the word global. That is just, following along. The typing wasn't the same, but hopefully you corrected that to be able to load your file name here and then unpack the contents of this text file into two arrays. One array is year, the other array is a temperature anomaly. So we're able to compute the mean value here. Why are we computing the mean value? If you recall, we use the mean values of the arrays X and, well, really array X is the one that appears here in this formula. And we don't have the formula. Let me see. We don't have the formula for the other parameter. So I'm going to now pull the lesson. There it is, linear regression with real data. So I'm going to scroll to the equation for linear regression. We have the whole derivation here, as we discussed last time. And again, show you the beautiful magic of this application called MathPix. I am able to use that to select an area of the screen. I'm going to select the area of the screen here with the equation for the other coefficient A0. This is the coefficient that represents the y-intercept of the line we're going to fit. And as soon as I take that little snip of the screen, I get the LaTeX code for that equation that was recognized there by the image that was captured. So that's fantastic. It was copied to my clipboard, so I can go back here, double click again on the markdown cell and add the equation for the y-intercept, or for the, let me just call it A0 coefficient is, and double dollar signs. And inside the double dollar signs, I'm going to paste what I obtained from the MathPix application. And when I execute that cell, now I have the beautiful equation rendered there in my markdown cell. So, in the past, we had to spend years learning the language for typesetting equations, and now you have some little artificial intelligence there that is able to do optical recognition of the characters and give you the code. Wonderful. And the reason I did that is now in this notebook, we have the equation for the two parameters that are needed to define the line that will approximate the data. And in the second equation, the mean value of the array dependent variable also appears. So that shows you that we're going to need to compute the mean value of both the year, that's corresponding to X here, the independent variable, and the temperature anomaly, which is the dependent variable. Okay, so we are going to need to do that. Well, we could, since we have learned to write Python functions, user-defined functions, we now can write a function to compute the parameters A1 and A0, right? And we may want to save the values of the means because we're going to need to use them. So we need to assign them to a name rather than just print it out like we did in input line 5. So let's compute the year mean, the mean value of all the year elements of the array. And now I'm going to use this function again, mean value with argument year. Remember, year is an array. And the only difference is with the previous line is now we are assigning the result of calling the function to a variable so that I can reuse that. I don't see an output because the important thing that happened in input line 6 is the assignment. Let's do the similar thing with the temperature anomaly. Temp anomaly mean is, I'm still going to call the same function mean value, but I'm going to call it with the array that has the temperature anomaly. All right, let's execute that. Now we have the two mean values saved together. Cool. Okay, but here is the thing. Whenever you find yourself writing a user-defined function for something that seems like more people than you might need, like computing the mean value of an array, you should ask yourself, does NumPy already have a built-in function to do that? Because most of the times the answer is yes. And you can Google a bit or look at the NumPy documentation online. But it turns out numpy.mean is a function. I'm going to use a question mark here to see what happens with that. NumPy.mean, it's showing me here the manual page of this function that does exist. NumPy.mean computes the arithmetic mean along the specified axis. It says along the specified axis because we can also use it with a multi-dimensional array. Of course, if the array is one-dimensional, it knows that the only possible way to compute the mean is along all the elements. But if you're, using a matrix or a tensor, n-dimensional, then you need to specify in which direction you want to compute the mean value. It needs an array A to come in. All of the other parameters, when it says here, it has an equal sign with a value, it means that that has a default and it's an optional parameter. So the only required argument is the array that comes in. It says here, array like is an array containing numbers whose mean is desired. So if I were to compute numpy.mean of the year, hopefully we get the same answer as we did with the user-defined function. And indeed, 1948 is the same value. So our function was good, but there was no need to do so much work. And also numpy.mean is even smarter than our function because it works in n-dimensional arrays, not just one-dimensional ones. So good. Right, so we learned that NumPy has a built-in mean function, and it has a bunch of similar functions that compute all sorts of things that you might need. And we've learned the hard way that sometimes you start writing a function from scratch, and then you're like, this seems like other people might find this useful. And you search a little bit, and of course, it already exists. And most of the times it already exists in NumPy or another library, and sometimes some people have written it and shared the code with others. So we can either use the function we wrote or the built-in, but now that we know that the built-in NumPy function exists, we might continue using it. And okay, so now that we have the mean values, we can compute our coefficients. Remember, the coefficients, if I scroll up a little bit, are used in the linear function that will approximate the data. This is just a line with a y-intercept and a slope. A0 is the y-intercept, A1 is the slope of the line. So we need to compute these lines. And the equation, let me just, to have it handy, copy this equation into a markdown cell closer to where I'm working, right here. Turn that into a markdown cell, paste just the equation so that I can have it right there handy to write the code that corresponds to that equation. So let's define a new variable A1. And what do we need? We need the numerator, a sum. Well, NumPy can certainly do a sum. We can already guess that. Let me show you that if you suspect that NumPy should have a sum function, I could type the first letter S, and then tab shows me, and I haven't showed you this before, that with a tab in Jupyter, I get like this drop-down menu with all of the NumPy functions that start with an S, and I can kind of scroll down and see, look at all the functions available to me. Wow, NumPy, it really has a lot of stuff. I learned that there's a sine and a hyperbolic sign. There's a sort. Oh, that's interesting. Split, square root, square, squeeze, stack. Okay, that sounds very interesting. But what I want is the sum. Boom, I click on that. I have the function sum. So that's very useful sometimes as you start typing the name of a function, then hit tab, and you're shown all of the functions that exist in this session that you're working in and have that match the name that you've started typing. So numpy.sum of what? All right, so the top in the denominator, what do we have? So you see here that in the equation, I've written y is the dependent variable. So for us is the temperature anomaly. And we have the sum from I equals 0 to n. But in NumPy sum, let me show you with a question mark now, the manual page, it computes the sum of an array over a given axis. And in this case, it's a one-dimensional array, so there's only one axis that is possible. In this case, the argument of NumPy sum is a full array. I don't need to loop over the I values from 0 to n. I can just type the name of the array here. What is the name of the array? Temp anomaly. That is our array that corresponds to the y values of our data. And then I need to multiply that array by what? The difference between the whole array of the year minus the mean value of the year. I could have used actually numpy.mean right here, but we've already saved it into a variable. We saved it into year mean, right? Because we're going to use it more than once. And so if we're going to use it more than once, we save it into a variable. So that is the full numerator, in fact. The difference between all of the values is the year. This is an array. This is an individual element. This indicates a sum. In NumPy, we can very compactly write this equation because NumPy gives us array operations. Inside this parentheses, we are subtracting one number to every element of an array. And then we're doing array element by element multiplication to obtain the numerator of that equation. So very compactly, we can write this equation here, numpy.sum for the denominator. And what do we need to sum? Well, in the denominator, we have the dependent variable, so that's year, and multiplied by the difference between year and year mean. I'm going to make this a little more compact since that line is long. Okay, there is my equation. Let me execute that. And let me print out the value just so that if you got something different, you can see print A1. That is the value that I get. And you can try it and see if you get something different. How would do compute A0? Well, let me just again copy the equation only closer to where I'm computing it so I can see it while I'm writing the code. There is the equation for A0. A0 is, okay, we are using the mean values here. The data in the y-axis is the temperature anomaly, and mean minus A1, which we computed in input line 11, times the mean value of the years. So in this case, it's a straight up equation with numbers, no arrays required here, and print A0 and see if you get the same value than I did. And now I want to do an exercise. Here's the exercise. The exercise is to write now a function that computes the coefficients A0 and A1, and then call that function. I'm giving you here like the basic structure of the function, the user-defined function that we want. You should write your own docstrings. We'll leave you here a hint, but what it's going to receive is 2 arrays. And it can receive the computed means, or actually you may decide to not send the mean values and compute the mean values inside, and that will be fine too. But what I do want is the function to return A1 and A0 like that. We can then compute the linear regression, the coefficients in the linear regression again and again with different sets of data. We encapsulate what we've just done into a function because we know that we're going to reuse it. Okay, let me start the timer right here and pause the recording after I do that. This is good practice, and we are going to want to use this function that we want to write here because we're going to do linear regression more than once. It's a pattern that we are going to apply over and over again. So for now, let's just note that in this case, I did compute A1 and A0, and I have those available to me. So once I have those available to me, I can compute a line that best fits our data. The line has y-intercept A0 and slope A1. So how do I get my, let's call it, I'm going to call it best fit. This is going to be the best fit to the temperature from a straight line that matches the data. And what is the independent variable? Well, it's the year. So the y-intercept of this line is A0, the slope is A1, and the variable that A1 multiplies is the year. On the right-hand side, I have the equation for the line with the variable year, and this is an array. This is a full array, so mind you, this is an array operation. Best fit is an array. Okay, I did a full array operation for every value of the year. I multiplied by the slope and add the y-intercept. So now what I can do is we can plot the values of our linear regression together with the values of the original data to see how it looks. So let's create pyplot.figure, and let's give it a fig size of, well, let's say 10,5. The 10,5 is width and height. So I know that my plot needs to be more or less wider than taller. And then I'm going to do pyplot.plot. What? Well, we have the data. Let's plot the data, year and temp anomaly. That's the data. We can give it a color. Let's say color is, I'm going to say red. And I'm also going to give it a line style of continuous line and a line width of just 1. So it's 1 pixel. That's a bit thinner than the default. The default, I think, is 2 pixels. There it is. So I've turned my camera off, and now I'm writing the next plotting command in the same code cell, which means this is going to be another line that will be drawn in the same figure. And now I'm still going to use year, but now I want the best fit regression. Now, best fit is the array that we computed above that corresponds to the line that approximates the data. I'm going to use color, now K for black. I'm going to use line style, 2 hyphens for a dashed line, and I'm going to use line width of 2. So that's going to create a little thicker of a line. I could already execute that and obtain a plot. So let me show you the plot. But we're going to fix that a little bit because we want always X label, Y label, and title. But you can already see the line and the data. So let's now fix our plot a little bit. pyplot.x label. What is on the x-axis? Well, that's the year. pyplot.y label, that is the temperature anomaly. And we're going to do something else. I am going to go back to the line of the plotting that produced the best fit, and I'm going to add here a label. Label is the keyword here for something that then I can use in a legend. I'm going to call this linear regression. And I know that this is too wide to display. So I'm going to enter a new line right after line style with a comma. So now, as you can see now, I have distributed this second plotting command in 2 lines. An extra line white space here doesn't bother Python at all. And it understands the command to be unfinished because we're closing the parentheses down here. This label right here allows me to use pyplot.legend to plot a little like overlay that is going to identify that line. Let me execute it right here. And as you can see, I have this little extra bit over here that says linear regression. It's showing me the dashed line that's black. And that's just giving me extra information in the plot that this line right here corresponds to the linear regression of the data. We have also some commands for the legend. I find it too small here. So why don't I say font size is, say, 16? What does that do? That made the size of that legend much larger, so it's more readable. And there it is, our linear regression that approximates the data.